So yeah, hi, welcome back. Today we are gonna solve this problem known as find in mountain array. Let's go through the problem statement. So yeah, you may recall that an array ARR is a mountain array if and only if array dot length is greater than equal to 3. There exists some I with 0 is less than I is less than array dot length minus 1 such that array of 0 is less than okay, so basically this is like increasing order. Either it should be in an increasing order or next half should be the decreasing order. So basically not a half, it states that some from 0 to ith index it is in an increasing order, and from ith to nth, like the last element, it is like in a decreasing order. So that is how basically the mountain array is being defined, and we are very clearly stated that array dot length should be greater than equal to 3. So yeah, so going forward, given a mountain array, this return the minimum index such that mountain array dot index is equal to target. If such an index does not exist, return minus one. So yeah, basically we need to find a target element in this mountain array, and we need to return the closest, like the first index where that element is present. That is what I can see here. So yeah, you cannot access the mountain array directly. You may only access the element using the mountain array interface. Mountain array dot get k returns the element at the index k indexed. Mountain array dot length gives the length of the array. So yeah, basically looking into this, like I think that they have passed the object of the mountain array. So to get the element k, like we need to get an index I in a vector. So we do nums of I. So basically here in the same way we need to do mountain array dot get k to get an element at an index k. And similarly we need to fetch the length. So like in vector we do it by doing nums dot length, and so here we need to basically get the length by performing this operation. So yeah, submission might making more than 100 calls to mountainarray.get will be judged as a wrong answer. So yeah, we need to be very sure that we don't make more calls than 100. So one thing is very clear, that 0 to ith node, it will be in an increasing way, and from ith to nth node it will be in a decreasing way, and the length will be greater than equal to 3 only. So yeah, and the next point is that how we take care of a vector. The same way we need to take care of the object here which has been passed here, and we need to make less than or equal to 100 calls. So let's go into the constraint. So yeah, in constraint it is very much given that the length will be greater than equal to 3. So yeah, we don't need to take care of the length part again. And here there is one more observation, that it should be less than equal to 10 raised to power 4. So, if it is 10 raised to power 4, we can't directly proceed with the linear search, because as we proceed with the linear search, it will fail directly there. So, it is very clear that linear search is not an option here. So, the other option which we have for searching is simply binary search. So, yeah, so let's move forward with binary search, I think. So, yeah, so how should we proceed in a binary search? So, so there is, as I can see here very clearly, that there is a 5 is a peak element, and like it can be known as the ith element, and from after the ith element to nth element it is decreasing. So basically we can note down few observations here. So let's note down observation. So first first part is increasing, second part is decreasing. Now, uh, next observation was linear search won't work. We need to proceed. We need to proceed with binary search. So these are the few observations which I see here. So next observation is basically like key. how should we use the binary search? Like, this is not like a simple binary search which we will be using. Obviously, we need to have some modified version of binary search to be used here. So what I was thinking was to like have a to get a peak element here, like we got a peak element, index of the peak element, and then perform a binary search on the first half, and then again perform a binary search on the second half. So this was my thought process. So I'm not pretty sure like how, if this will work or not, but yeah, let's move forward. And if in the middle, while performing this binary search, if we end up finding the element, we will be returning that element that yeah, this is present at this in given index. But yeah, to be fair enough, like if we return the index while performing that binary search, it won't make any sense, as there might be duplicacy at it might be present in the first half also, and it might be present in the second half. And what if we return the element in the second half? So that will cause a problem for us. So yeah, let's first go and perform that peak element way, and then uh, perform in first half and second half. Okay, so let's have a solution written down here. Thought process, basically a thought process. So first find peak element, find peak element. Second, perform binary search in left part of peak element. Third will be perform binary search in right part of peak element. So yeah, so this is what my thought process is for now, and I'm not pretty sure like if this will work out or not, but yeah, let's give it a shot. So I commented it out. So now how to get a peak element? So yeah, basically we need to have like int l is equal to 0, like this is low, and int h, let's get that as int n also. So yeah, so that will be mountain array. Mountain array dot get probably I'm not sure, length, yeah, dot length. So we got the length. Then this will be also h. So yeah, we need to make it length minus 1. So now we got like the peak last element of and the first element. So now like performing the binary search, while less l is less than equal to h, and defining mid, m is equal to l plus h minus l slash 2. We got the mid element. Now performing the operation, like if so one thing is very clear that if this part is suppose increasing, so let's say here like the m is at the, okay, how many elements are there? 7 elements are there. So it is m is like here. So if right part is bigger, then obviously the peak element would have been in the right part. So if m is less than n minus 1, and then mountain array dot get, let me copy this, mountain array dot get m is less than mountain array, okay, wait, mountain array dot get m plus 1. So we need to make move the l one step further. L is equal to m plus 1, else if m is greater than 0. And what if like m is suppose here, the array, so let's expect that array is too big and m comes out to be at this position. So if m is here and m minus 1 is bigger, so we need to move the h to the m minus 1 part. So else if m is greater than 0, and mountain array dot get m is less than mountain array dot get m minus 1, we will be moving h to h is equal to m minus 1. So this I think makes sense. And like else, if else we can have like if both of them are not equal, that means that is the peak element which we have got, and we need to break out from there. So let's store the peak element index. Int peak element index is equal to 0. For start, let's have it like at a 0 index. Okay, so peak element index, so it will come out to be m, and we need to break out from here. Let's print that peak element index to be sure that we actually did this correctly. Index. And let's return some value for now. Okay, so let's try it out. Okay, we missed out here something. So we are getting at 4, which is correct. 0, 1, 2, 3, 0, 1, 2, 3, 4. Yeah, that's correct here. Now let's take for this example. We have got it for 3 index, 0, 1, 2, 3. Yeah, so perfect. So we got like peak element index. Basically, we got this index. Let's obviously we need to search it in the first half first, and then in the second half. So that will make sense, right? Like if so why I am saying so is because left index will come first and then the right index will come. So obviously while searching for that part, we need to be very sure that we also pick in the left part the first occurrence of that number, because I think the duplicacy is allowed. And let's say like uh, say okay. So yeah, and on the left part there will be only single occurrence, and in the right part there will be only single occurrence, as it has been stated here that it will be strictly less than or strictly greater than. So we don't need to care about the equal to part. Okay, so that's very much clear again. So now let's start with that part. In now again, let's L is equal to uh, let's have it as 0 obviously, and H is equal to uh, peak element index. Element index. So we got this like L is equal to 0 and H is equal to peak element index, while L is less than equal to peak element index. Sorry, H. And now again we will have int M is equal to L plus H minus L slash 2. So we got like the mid index if uh, mountain array dot get m. From here, if mountain array dot get m, okay, is less than let's say target. Okay, let's have it equal to first, so we can directly share the index as soon as we get it. So return. Okay, so one thing I observed, like we can reduce the call of this by having a like we have only 100 times options, so we are like continuously getting it. So like to reduce it, we can have int element here, and we can store it directly in here. So this will help us to reduce the call also. So like yeah, int element. And one more thing we can do here is like since we are traversing here, okay, so we are like fetching the m plus 1 index element and m minus 1 index element. Okay, so what my thought process was like to have it in an unordered map. But yeah, we will try to uh, reduce the number of call going in future. Let's for now don't worry about that thing. We can just store here, and like we can do one more thing for now, like unordered map of int comma int and let's have it as a map mp, and like storing that value inside this mp of m is equal to element. So what I did was like I stored that occurrence into this number, so which you can use in future also. Okay, so yeah, so now uh, again here we will do the same thing. If mp dot find mp dot find, we got it at index m is not equal to mp dot end, and like here we are defining int element, so element will be equal to mp of m. Else we can have it like element is equal to element will be equal to mountain array dot get m. So yeah, now we got the element. Okay, now let's have here call again. Let's give some space for if element is equal to let's say target, which we have been asked for, we will simply return m here. Okay. Else if element is greater than target, we will have to go L is equal to m plus 1. Else, else we will have to perform h is equal to m minus 1. Okay. So this is more of like left part which we solve in. Like this will take care of this part, left part. So we solve for the left part. Now going forward, we need to move for the right part. So here the things will turn little bit different, as we need to perform binary search on the descending order array. So we need to modify our binary search as per that thing. So yeah, so now again L will be equal to peak element index. So as we took care of this element till here in first half only, so now we need to take care of this part. So we will start from the peak element index plus 1. So peak element index plus 1 plus 1, and I we don't need to store here this element into the map. Reason being because I think that we have solved for the left part and we are moving for the right part. So that's this element duplicacy will not this index will not come again in the right part. So that is why. So L is equal to this and H is equal to let's have here index as n minus 1 n minus 1. So yeah, while L is less than equal to H. Okay. So again, we will be having copying this statement here. Perfect. Now, yeah, now the things will start if element is equal to if element is equal to target. Let's return that m. Else, if element, sorry, if element is less than target. Let's say it is element is greater than target. So what means element is greater than target? So if you take, let's say this is the array 531, this element is the one we got it at the mid, let's say, and this is bigger than this. So I need to make L is equal to mid plus 1. L is equal to mid m plus 1. Else H is equal to m minus 1. So wait, let me see it that again. I think we need to do it reverse, but why am I doing this in that way? So like this is the part. Okay, let's say we are searching for uh, let's have an example here not get confused. So let's say have here 6 5 4 3 2 1. Let's say we are searching for 2. So uh, this is of size 6, 0, 1, 2, 3. It will come here. So now since 2 is less than 3, 2 is less than 3, target is less than 3, we will move L is equal to m plus 1. So that's somehow like, okay, wait, 1, 2, 3, 4, 5, 6. Okay, let's say we are searching for 2 again. So here 2 is less than this. So we were doing, okay, we need to do here opposite, I think. Minus 1, h plus 1. So let's see if that makes sense. Like, this is the part 1, 2, 3, 4, 5, 6. And let's have like L is equal to 0, H is equal to this. And this is 6 length, 0, 1, 2, 3. M will be here. And since 2 is less than 4, so 2 is less than 4, we are moving H is equal to M minus 1. Now here what was happening, here this is there, and let's say H is at M is here, M will be here, M will be here, 2 is less than 3. So target is less than 3. So we will do H L is equal to M plus 1. I think we wrote it correct only, I think, yeah. So L is equal to, we need to move, if it is 3, we need to move L is equal to M plus 1. So it will come here. And what if we are searching for like 6? So here the 6 is greater than 3. So H will become M minus 1. H will come here and L will be here only. So M will come here, and again 5 is less than 6. 5, 5 is less than 6. L will become M plus 1. Oh, wait. Element is greater than 6. Okay, let's search for 6. So M will be here. M will come at 3. So M will come at 3, and 6 is greater than 3. 6 is greater than 3. Element is greater than target. H is equal to M minus 1. So H will go here and L is equal to M plus 1. Okay, so I think this is how it should work. Let's dry run it here again. So it is 3. We are searching for 2. Okay, 2 is not greater than element is 3. 3 is greater than 2. 3 is greater than 2. H is equal to M minus 1. Wait, I think somewhere something is getting wrong here. Let's figure it out. mm, L is equal to M plus 1 we are doing, or element is greater than 2. Here what is the thing is that if the element is, okay, let's try to catch 6. 6 is greater than 2. So if element is greater than, if target is greater than element, if target is greater than element, if target is greater than element, we are moving H is equal to M minus 1. Okay, yeah, if target is greater than element, okay. If target is less than element, we are going to move L is equal to M plus 1. So yeah, this is how it is. Now let's run it once so that we can get a proper idea. Yeah, let's return minus 1 here for a not found element. Okay, now let's try to submit it. So yeah, we are getting a wrong answer for this one. So why it's failing, let's try to get it. So first of all, we got a peak element at a index 4, which is very much correct. Okay, and the target is 2. Target is 2. So I think it should have found it, but let's try to see like why it did not found it. So L is equal to 0, H is equal to peak element index, while L is less than equal to this, MP dot found. And if element is greater than this, so we got like, okay, let's use this test case. and try to figure it out why it did not went as we have planned. So let's try to print here m. Okay, see out m and l. Okay, so okay, so like peak element index is uh, peak element see out m. So we got like 4 and 4 slash 2 is 2. So we got like at index 2. So this is 0, 1, 2, 3. This is 4 and we got at 2. So we got at 3. Okay. So we got like at 3 and let's see what element we are getting. I think we are having some, yeah, yeah, perfect. So, so we got like 2 here. Okay. At 2 index we got 3. Okay. Element is since greater than target. So 3 is greater than target. L3 is greater than target. Okay, I think we have done something wrong here in binary search in my thought process, I think. So if element is greater than element, this is greater than this, then we need to do h is equal to m minus 1. Minus 1. L is equal to m plus 1. So now let's run it again. Let's try to submit it again. Okay, now the target was 2 and we did not found it. Okay, so now what have happened here, let's see again. So 152 and we got the peak element correct again. So now like it was 0 comma 1. So let's try to print here also like what is happening, we will get an idea. So let's not print it here, let's print it here. Yeah, so now let's again run it. Let's use this test case. Okay. So what's basically happening is that first of all I'm not okay, why this is going to, okay. So what here is happening is that L is getting at peak element index plus 1. So we are getting at L is equal uh, to 0, 1, 2. Okay, 2 plus h minus L slash 2 we are getting. Okay, since L is equal to this, so I'm not sure why we got here this thing as, okay, let's print here once, see out L, see out H. So okay, let's print that last and let's try to see 2 and 1. So somewhere I think, yeah, okay, I got it. So we did not did here h plus 1 run. Okay, I did it. Oh yeah, we did it correct. So yeah, that's all from my side. I think we were able to solve this in like 30 minutes. That's not pretty good, but yeah, we did it. Okay, yeah. Thanks. Thanks. That is it from my side. Thank you.